Hello, everyone. Today we will introduce the system we developed at the Voice Privacy Challenge 2022. The contestants of our team are from Xinjiang University in Urumqi, China, Kyoto University in Kyoto, Japan, National Institute of Information and Communications Technology in Kyoto, Japan, and Kuaishou Technology in Beijing, China. Today, the security of speech data has received many concerns from researchers. Voice privacy protection has become a top priority. Therefore, different solutions have been proposed to protect the speaker's privacy, and one of the main approaches is speaker anonymization. Speaker anonymization technology aims to suppress speaker identity information in the speech signal. Specifically, according to the Voice Privacy 2022 challenge, the speaker anonymity system needs to satisfy output of speech waveform, conceal the speaker identity, the linguistic content and paralinguistic attributes should be preserved, and ensure a one-to-one correspondence between speakers and the sued speakers. In previous work, reference 2 proposed an anonymization method, which modifies the X vectors by selecting an X vector from an X vector pool as a sued X vector. This method is the first baseline system in the Voice Privacy 2022 challenge, inspired by our previous work. This paper proposes two modifications to improve the X vector-based baseline. The first one is adding the adversarial noise, and the second one is eliminating speaker information in a transformer-based ASR system. This section we will introduce our proposed methods, which will modify the X vector based on the baseline system. As shown in Figure 1, the first method we proposed is based on the first baseline system improvement of the Voice Privacy 2022 challenge. The main improvement is that the original pool of X vectors is replaced by an adversary anonymization, as shown in Figure 2. We propose the second method. Compared with the baseline system, we use transform-based sequence-to-sequence speech recognition architecture to extract speaker embedding. Both of the approaches from framework are almost the same. The framework is performed in 3 steps: feature extraction, X vector anonymization, and speech synthesis. Feature extraction includes extraction of the speaker X vector, which is based on the TDN, the fundamental frequency, and bottleneck filter from the input speech waveform. The X vector anonymization module is an essential part of the anonymization system. The speech synthesis uses an acoustic and narrow waveform model to synthesize a speech waveform from the anonymized X vector and the original bottleneck and fundamental frequency filters. The first approach is based on the concept of adversary perturbation. Previous studies show that adding some small perturbations to the original input can mislead the classified system to get error results. The essence of the idea of adversary perturbation is consistent with the idea that we want to modify the speaker anonymization method based on the X vector. Therefore, we use the method of adding perturbation to anonymize the speaker. As shown in Figure 1, we proposed a new anonymization method based on adversary perturbation. The process of our proposed adversary anonymization method can be formulated as follows, where the xi denotes the original x vectors of speaker I, and the anonymized x vector of speaker I is yi. Considering the amount of computation required in the anonymization process, we borrow the method of non-targeted attack. In other words, adding the adversary noise to create a fake speaker and hide the original speaker's identity. Figure 2 shows the second method of our anonymization systems. In reference 3 and 6, it is shown that the output of the acoustic filters by the encoder of the transformer can effectively show the classification characteristics of the speaker. Therefore, to some degree, the ASR embedding can represent speaker identity. And we replace the extractor in baseline with the transformer-based ASR system. This figure shows the second method to extract embedding of target speaker. The whole model is a speaker adaptive ASR, which includes multi-head self-attention, positional encoding, and position-wise feed-forward networks. We can extract the speaker embedding as the output of the encoder, and the decoder will output the target speaker identity label. All datasets used in this experiment were based on the VoicePrivacy 2022 challenge, and the detailed dataset is shown in Table 1. We used LibreSpeech 330 for training and subset of LibreSpeech and VCTK as development and test sets. The main part of our experiment was conducted same as the first baseline in VoicePrivacy 2022 challenge. For the text method, we extracted the embedding from the encoder of the transformer-based ASR systems, and we adopted the transformer-based speech recognition model, which named as ASR speaker. The ASR speaker model required for embedding extraction is trained on the LibreSpeech train clean 100, but based on the multitasking train method following reference 6 and 7 with the speaker ID and label. For the evolution, attackers were assumed to have access to the unanonymized speech and anonymized speech utterances. Therefore, there are these three attack scenarios are as follows. The Table 2 shows the ERO baseline and our proposed methods. There are three datasets introduced earlier to participate in the test. As shown in Table 2, the anonymized speaker has a lower performance on the same speaker. The robustness of Model 1 and Model 2 can be further improved. Model 1 performs better on the test datasets. Moreover, in Model 2, the performance on all development and test datasets approach the baseline. Compared with the baseline, a small calculation ability is needed for Model 1 and Model 2. The Table 3 shows the results of the pitch correlation and gain of voice distinctiveness achieved on data processed by proposed methods at baseline. Model 1 performs well on the pitch coordination, which is better than the baseline. Moreover, the pitch coordination of Model 2 almost equals the baseline circles for the gain of voice distinctiveness. Proposed methods still have room for improvement. Table 4 shows that the ability of the proposed anonymization system to preserve linguistic information is known as weak than the baseline system. And the results show that the speech content after proposed anonymity has relatively complete preservation. Moreover, our proposed Model 2 system has simplified the pipeline of baseline system. In summary, we test two methods to protect speaker privacy. Moreover, we extract speaker embedding from the end-to-end ASR system, and experimental results prove that both methods can be used for speaker anonymization tasks. Lastly, this is the reference list. We thank you for your listening.